Hello everyone and welcome to my virtual presentation. Today I'll be talking about work I did as a summer intern at Mitsubishi Electric Research Laboratories on fail-safe spacecraft rendezvous on near rectilinear halo orbits, which occur in cislunar space in the Earth-Moon system. In addition to considering this alternative mission concept, we are also extending prior work presented at last year's ACC and CDC conferences. So rendezvous involves a controlled spacecraft called the chaser, which aims to approach and remain near a target body. This often represents another satellite or something like a natural asteroid or a comet. It's important for several reasons, but the case study of interest in this paper is motivated by future human spaceflight. There will be a manned space station located on a near rectilinear halo orbit, as shown in the top right over here in green. Here's the moon, here's the station, and here's the Earth. This station on NRHO, called the Lunar Gateway, will serve as a stopping point for manned space missions to the lunar surface or into deeper space. Moreover, this still remains a hard problem. Orbit dynamics are not that intuitive, and in the last 10 years, we've still had rendezvous failures despite the use of automatic approaches. So if we're trying to do this autonomously, it's going to be even harder. And since we anticipate more complex missions in the future, it's important to develop a framework or system that can handle safe rendezvous autonomously and robustly. The goal in Abort-Safe rendezvous is to minimize the performance metric while satisfying the safety constraints. That performance metric might be maneuver delta V, which is a proxy for fuel consumption, or thruster on time. We want to reduce the amount of time that thrusters are on to reduce the risk of thrusters getting stuck in an on position, and also such that less loads are imparted on onboard instrumentation. The safety we're concerned with is such that even if you had a partial or total loss of propulsive capability, there would at least exist one passive or active abort maneuver that allows the vehicle to avoid collision with the target. In practice, solutions are typically automatic in the sense that a vehicle will follow a pre-written set of commands like a script. Such methods however, are not flexible in general and will work for a limited set of approaches and missions. Also, these techniques are not autonomous, which may be required for complex or deep space missions and for scalability as rendezvous becomes more commonplace. Now, rendezvous is typically split up into two approaches. The initial approach is concerned with passive safety, where we want to ensure that the chaser is not at a state where natural dynamics would lead to eventual collision with the target. And as the chaser gets closer to the target, the final approach begins where we want to maintain active safety, where we need to be able to show that at the current chaser state, at least one powered abort maneuver would exist. Now, our prior work dealt with both of these safety aspects and generalized some of the prior research. Research in this area has obviously been studied. However, these methods generally offload the entire problem to the solver, and they require solving a large optimization problem. In our approach, we use reachability theory to determine what are the unsafe regions of state space, kind of illustrated by this region right there. And then we use local convex constraints in the online MPC formulation to separate the current chaser spacecraft from the unsafe regions of state space, thereby remaining safe and ensuring that at least one passive or active abort maneuver would exist. We demonstrated this concept on our Earth orbiting spacecraft in our ACC and CDC 2020 papers. Now we are extending this to another type of orbit. So just recall that we want to be safe with respect to a partial or total loss of propulsive capability. Then by using robust backwards reachable sets with control sets instead of disturbances, we can actually obtain the set of states that enter the target set no matter the control used. So you'll notice the for all controls argument right over here in the construction of the set. We compute these sets through the backwards recursion. For example, this new gray set represents the set of states that would enter that target set no matter the control used in one time step. Here we have the set of states that enter that successor set no matter the control used, and you keep working backwards for some safety horizon of interest. Then, if you take the union of all of these guys on the right, you would end up having the set of states that fail at a specific final time. However, we have to recall that the relative dynamics are LTV, and they change with time as the target is in different parts of its nominal trajectory. Therefore, we must take a union across variable final times to maintain safety with respect to this LTV system, as shown by this equation over here. Then lastly, if we're considering various failure modes, we must take another union across these control sets as shown over here on the bottom right. Naturally, the number of sets in this union can in general be quite large. And when that control set over here is empty, we obtain the set of passively unsafe states. In our prior work, we used MPC to avoid the unsafe regions of state space. But MPC doesn't generate realistic control signals since many times thrusters can't just use continuous controls and we need to reduce the time that thrusters are actually on. So in this paper, we had a couple of goals. The first is to improve fuel efficiency and reduce the amount of times that thrusters are on. And also, we wanted to demonstrate this on NRHO because of future mission concepts. Now, ideally, we would solve the safe ΔV optimal control problem while trying to reduce the thruster on time, but this is quite challenging. In fact, reducing thruster on time would generally require adding integer decision variables, which quickly becomes intractable for online implementation. So how do we do this? Well, we tried a few approaches, but we realized we were sitting on top of a convenient solution the whole time. We can leverage the passive backwards reachable sets from our prior work. In fact, we can define a goal set, shown here in blue in G subscript F, and compute the passive backwards reachable sets from this guy. And we call these sets the coasting sets. Then the goal would be to steer the chaser into the blue sets in some way while avoiding the red portions of state space, such that once you enter these blue sets, you can just naturally coast and drift into the desired goal set, thereby doing a hopefully fuel efficient and also a rendezvous that uses the thrusters less often. So we'd be exploiting natural dynamics better, and we'd be satisfying both of our goals. So we first specify the time at which we want to arrive, or the maximum number of sets we want to coast. We use our prior passive backwards reachable sets to construct the coasting sets. Generally speaking, the coasting sets and the unsafe sets are going to have a non-empty intersection. This means you can coast into the goal set first, and then you could passively drift into the target set after, or vice versa. In this work, we use MPC to drive the chaser into the set difference of these guys, but without explicitly computing that set difference. Now, since we have an LTD system, we just have to be careful about which coasting set we are targeting at each moment in time, and this is handled through this constraint. If you don't target the right coasting set, you might enter the goal set at the wrong time, or you may not even enter it at all. And then naturally, the constraints are initially infeasible, and thus we can use slack variable penalization as well as constraint tightening to drive the chaser into the coasting sets. So now we're actually in a good spot. With our coasting method, MPC can give us good thruster behavior while maintaining safety. We see here the standard stage and terminal costs, which are also functions of a slack variable. These are going to be used to soften those coasting constraints I talked about earlier. The constraint function G will include those coasting constraints, as well as all of the convexified safety constraints such that the chaser is separated from the unsafe sets. In our sims, this function depends only on the mission phase. In our results, we only tried coasting in the initial approach, as shown over here, where passive safety is required. As such, during this phase, if the chaser is not inside of the right coasting set, the standard safe MPC solution is used, right over here. If it is, the control is turned off. After coasting to the goal set, the final phase begins where active abort safety is maintained. We incorporated a line of sight constraint in this paper as well and use a standard safe MPC solution. Our method is flexible, and in this paper, we show results for a realistic NRHO target. Both the target and the chaser are in orbit in the Earth-Moon system. Our dynamics model is a high-fidelity, full ephemeris one, which means we're taking into account all dominant perturbations. In this figure, we show the geometry at hand. We have an inertial frame centered at the Earth-Moon system barycenter right over here, depicted by the black arrows. We also have a synodic frame, which rotates with the line connecting the Earth and the Moon, shown here by the red arrows. We can clearly see the chaser's position, the target's position vector, as well as the relative position of the chaser with respect to the target. Our aim here is to drive that relative position vector to 0 while maintaining safety and leveraging the coasting sets. I also want to quickly show you what a family of southern L2 halo orbits look like, as shown over here. The Moon is clearly visible in the middle. As you can see, they're kind of funky. Now I'll show you some results for the mission scenario considered. Here we show the results of the coasting algorithm for an approach at Perlun, which is the closest point of the NRHO to the Moon. We've set the coasting duration to be 6 hours long, given the initial time. And here on the left, in blue, is the new solution with the coasting arc. We can see that the coasting arc is indeed almost 6 hours long by looking at the plus on the right, where we see that for the most part, the control is 0 in the 6-hour window. And when we zoom in, only 2 burns were required to enter the coasting set, and from then on, we just drift naturally, following this blue trajectory until we enter this green goal set. In red over here, for comparison, we show the original safe MPC solution from our prior work. So both methods are obviously safe. On the top right, we can see how, with our new coasting method, states along our initial trajectory passively drift and never hit the red ellipsoidal target set, so we are in fact passively safe. Now, though the coasting MPC uses larger burns, as we can see from the bottom two plots, since only 2 burns are used before switching phases, the ThA savings during the initial approach are significant. For the same prediction horizon, the coasting algorithm is much more efficient as it exploits natural dynamics more. Now lastly, for a standard safe MPC solution to yield similar behavior as what we see with the coasting sets, we would need an enormous prediction horizon, which simply is not tractable for online usage. Here we show another example at Paraloon, but where the coasting arc is now 10 hours long. The burning arc portion is shown in blue, while the coasting arc is shown in green. Again, the ThA is very small for this maneuver. Here are the results for Rendezvous at Apolloon. Clearly, the dynamics are different as the trajectory is almost a straight line. Now, once we enter the goal set, the active safety portion starts. And here, we're simulating a case where the only available control after the failure time would be given by these constraints on the left. The failure mode is notable because there is no braking maneuver that can be made when looking at our initial condition, which is right here, and we're trying to move in the positive y direction. However, the chaser can't slow down along the y-axis. Hence, at the failure time, which is right here and right here, a z-directional burn must be engaged to avoid a collision. It should be noted that none of these maneuvers are pre-planned. The MPC found them since the chaser was in the safe region of state space. So in conclusion, we developed a fuel-efficient and fail-safe control policy for Rendezvous on generic time-varying orbits. We targeted and exploited coasting sets, which allowed us to reduce fuel consumption and thruster on time. And finally, we studied Rendezvous scenarios that were safe for a target in a high-fidelity, full ephemeris, and quasi-periodic NRHO. And that's it. Thank you very much for your attention. Feel free to contact me if you have any questions.